All right. So, yes, Ashton, as always, we'll go over homework, but we'll do that at the start here of the recording. So, welcome to another lovely week of calculus. Or, oh, sorry, calculus. How about statistics? Wrong class. All of a sudden, there was that panic moment. You're like, wait, what? Calculus. Um, but yeah, so last time we were talking about hypothesis testing and how we're testing, how we test one sample and all that. And we'll continue talking about that, but we're going to extend it today to how do we test two samples against themselves? Like, what if I want to compare weights of male babies to female babies, right? I want to see if there's any kind of a difference there. We want to be able to compare two different populations. And that's what we're going to do today. We're going to see how do we adjust what we've done in terms of hypothesis testing to take care of two different populations. So that's my goal. But as always, I'm more than happy to go over some homework. So what would you guys like to look at and talk about? Is there anything from the homework or previous stuff that we'd like to chat about? Okay, so Ashton, you said you want to look at hypothesis test for a single population mean. Okay, do you have a specific problem in there that you want to look at? And then Carolina, I do see, so can we look at problems 6 and 7 on chapter 8 sample size for confidence intervals? Definitely. All right, and then lady, I see your number 4 in there as well. Okay, so Ashton, it doesn't really matter. Any of them are good. Okay. All right, well, let me do this. Let me go ahead and share the screen again, and we'll go take a look at those homeworks. We'll start with the ones from chapter 8, and then we'll move to the ones from chapter 9. All right, so hopefully everybody can see my screen here. So confidence intervals, sample size, boom. All right. So I've got on my list 4, 6, and 7. So let's go see what those guys look like. So here's number 4. All right. So you want to obtain a sample to estimate a population proportion. Based on previous evidence, you believe that the population proportion is approximately 0.67. We would like to be 96% confident that your estimate is within 2% of the true population proportion. How large of a sample size is required? Okay, so to do this, we need to know basically how we find the error bound maximum and how that is compared to the sample size and stuff like that. And so to tackle this one, we need to recognize a couple things. So first of all, we need to know, are we looking at a test for means or a test for proportions? Are we looking at an interval for means or proportions? So what's the answer to that question?
Proportion.
Okay, so what tells you it's proportion? Thank you for that, by the way. I mean, check it out. It says we want to estimate a population proportion. So it tells us right there This is proportions. All right, so why do we need to know? Why does it matter that it's proportion versus mean? Because there's a reason I asked, right? It's not just because. Okay, so like Willie puts in the chat, it's a different calculator thing, truth, right? When we do the tests, remember that we do, like if we're going to test a hypothesis testing, there's, we either use a Z test or a T test for a mean, or we use the one prop Z test for proportions. But when it comes to confidence intervals, the reason that we need to know is we calculate our error bound differently. There's a different formula for error bound if we're talking population or we're talking mean. Okay, so let me write down some numbers here. I think I got all the information that we need. So things to pay attention to. We know that the population proportion should be around 0.67, and we want to be 96% confident. So that's our confidence level, right? And we want to be within 2% of the true proportion. All right. So let's go to the whiteboard here. Okay. So if we go back and we look at the error bound for proportions, the formula for that one is a little bit different. Anybody remember what it looks like? So it's not the same as what we just did. If you look back at that quiz, the one that we did there for the error bounds, that was for the mean. So what's the difference here? Okay, so Carolina has the Z alpha over 2. All right, and then times P prime Q prime over N squared. Okay, yeah, cool, square root, thank you. All right, so thanks, Caroline, that's exactly right. So this time we're gonna take our Z of alpha over 2, and it's gonna be the times the square root of P prime times Q, not G, P prime times Q prime over N. And just so you know, Carolina, if you want to do square root in math, we usually would do something like this. So it would look like, I'm typing it into the chat box. Please type SQRT or square root. Anyway, all right. But regardless, let's come back to this guy. So in terms of this, we don't care about the error bound. We actually want to solve for N, right? But let's look at what all these different things are. So the error bound for our proportion, this is how much we want to be okay with being off by. And so that's the one that we're going to be okay with that being 2%. Okay, the Z alpha over 2, we actually know what alpha is going to equal. And alpha in this case is going to be 0.04 because we were told we want to be 96% sure. Okay, so we know the alpha. We also know P prime, right? We were told that we should expect that equals 0.67. So we know that number, which means we can also get Q. So what's Q prime going to equal here? What's the numerical value for it? Of course, that means we have to remember what Q prime means. What is Q prime? And remember, an answer of I don't know is perfectly acceptable. I'd rather that than no answer. Okay, so Willie just put in the chat box 1 minus P. So yeah, 1 minus P prime. And it is, it's 1 minus P prime. So in this case, that number is 0.33. But what it actually is, if you want to think about it, if P prime is the probability of success, Q prime is the probability of failure. All right, so we have all the information we need. We've got everything we need in order to calculate n because we've got, or we can at least find values for everything but n. All right, so Willie, so what do we do if we don't have, when you say neither, you mean the P prime or the Q prime? Yeah, okay. If you don't know what they are, does anybody remember what the trick is that we play? There is a value that we plug in if we don't know. Does anybody remember what it is?
It's that 1E or 1E99 or something.
So the 1E99 is what we use for an upper or lower bound, which isn't going to work for a proportion, but you're right here that we do use that a lot for if we're not really sure of a thing. But we put in 0.5, as Lady just put in the chat box, and we just assume 50-50 because that's going to give us the biggest possible n. It just means that we're going to potentially err on an overshot, but we'll still have enough to guarantee that our sample size is good enough. Okay, so if you're not told, if you have no clue, there's no context of what P or Q is, then you just go with both of them as 0.5. But good question. All right, well, here we go. Let's see if we can figure out what we need. So if you solve this for n is actually equal to P prime times Q prime times Z of alpha over 2 divided by your EVP squared. So that's what the algebra does on this. And I'm pretty sure that somewhere along the way I showed you this formula. I know it's definitely in the book. But this is what we're going to go with and where we're going to plug in our numbers. Okay, so we're going to have n is equal to P, 0.67, times Q, 0.33, times, okay, well, our error bound is 2%, so 0.02. But then we need to get our z of alpha over 2. Since alpha was 0.04, that means we need z of 0.02. So we'll get that by using the calculator. So let me share my calculator. So hopefully you're all seeing my calculator right now. So we're going to go to distribution, and we're going to do inverse norm. That's how we want to find z-scores. So we're going to go inverse norm. We put our area. Okay, so I wanted 0.02. And we're going to do it with a mean of 0 and a standard deviation of 1. That's how you get z-scores, is by using the standard, which is a standard mean of 0 and standard deviation of 1. Okay, so we hit enter. And there's our z-score. Now this one says negative because I went with the smaller number. If I'd gone for the bigger number, it would have been a positive. It doesn't really matter. We're just going to put it in as a positive, but 2.0537. Okay, so 2.0537 is what we're going to put in for our z value. Okay, so you can just use inverse norm. That's probably the easiest way to get it. There are, tables and things that you can use as well, but we'll just do it this way because, yeah, it's easier. Okay, so I'm going to punch this into my calculator, see what it spits out. And I got a number of 2,331.324. But for a sample size, it has to be a whole number. And so what we're going to do is we're going to round it up, always round it up to 2332. Because you can't have a fractional number of people that you ask or anything like that. And so since we need to have at least this many, we are going to err by going bigger. All right, well, there you go. That's how we find the sample size for a proportion. So before we go look at the next one, any other questions on this guy? All right. So let's go ahead and switch back to this one. So that was question number 4. And then the other ones were 6 and 7. So let's see what those guys look like. Oh, good. Okay. So this one says, we want to obtain a sample to estimate a population mean. Based on previous evidence, you believe the population standard deviation is approximately 57.6. You would like to be 90% confident that your estimate is within 3 of the true population mean. How large of a sample size is required? All right, so same question as with the first one. Are we doing a mean or a proportion? And it should jump out at you. Yeah, it's yelling at you, right? We want to estimate a population mean. Okay, so we're going to estimate a population mean. Again, we needed to know that so that we use the correct formula, right? Because we find it in a slightly different way. All right, well, here we go. So we are given a population standard deviation, which means we're using z-scores again. So let's go back to the whiteboard. Now this time, if we go to the EBM, and it's a z of alpha over 2 times sigma divided by the square root of n. So like that's what we were using when we did our confidence intervals, right? So again, we're solving for n. And so n is going to equal the z of alpha over 2 times sigma divided by our error bound maximum squared. All right, now all this other information has been given to us. We were told the sample standard deviation, or the population standard deviation of 57.6. We know we want 90% confidence. So that means that alpha is equal to 0.1. And we want to be within 3. That was our error bound maximum. Okay, so we just have to find z of 0.05. That's our alpha over 2. Once we get that number, then we'll be good to go. All right, so let's go get that from the calculator. Again, this is one that you're going to get to know this number really well, but we'll go ahead and do this. So we're going to do inverse norm. I'm actually going to cheat a little bit and just recycle this, because instead of 0.02, I want 0.05. Just enter. All right, so that's minus 1.6448. All right, so 1.6448 is what we're going to put back into our value over here. All right, well, let's plug everything in. So 1.6448 times 57.6 divided by 3. Take that whole thing and square it. So again, this is just a calculator exercise. Let's see what mine says. I got 997.306, which again, we're going to round up to 998. All right, thanks, Bruno. Thanks for letting me know. All right, so there you go. But I want you to look at these two and compare them. And you can see that they're actually very, very similar. It's just we started with a different formula, so we need to know different things. But it's just a matter of finding those things and firing them in. All right, it's just there's a very different formula for proportions than for means. All right, so cool for that one. So I think I'm probably going to skip number 7, but let's just take a look at it real quick, because I'm going to guess it's similar to these. Okay, good. Let's see, so 7. You want to obtain a sample to estimate how much parents spend on their kids' birthday parties. Based on a previous study, you believe the population standard deviation is approximately $60.5. You would like to be 99% confident that your estimate is within $1 of average spending on birthday parties. How many parents do you have to sample? Okay, so is this proportions or means? And this one's a little bit tougher because it doesn't just say you're testing population mean or testing population proportion, right? But what are we doing in here? Is this a means or proportions question?
Proportions?
All right. Why do you think proportions? Thanks for volunteering, Kira, by the way.
Probably not, actually.
Probably not. Well, we have a
I
couple in
was
the chat
thinking
box.
there was a comparison in there.
Okay. So remember that what we're looking for, means are averages, proportions are percentages. So are we looking for what percent of parents spend money on their birthday parties? Or are we trying to figure out the average amount spent? And this one, if we,
Average.
yeah, it says here, so we want to estimate dollar of average spending. So unfortunately, this is more real world, or fortunately, this is more real world, where we're not necessarily told specifically, hey, test proportions or test means. We have to be able to determine it, but the wording will always tell you. And a really good way to kind of remember or to help push you in the right direction is kind of like what I first said about, are we looking for a percentage of people that are doing something? Or are we looking for how much they're doing it? Okay, because anytime it's a proportion, you're looking at a percentage of, right? Like if we're gonna make the claim, we're trying to find out what percentage of people work overtime. Okay, that's going to be a proportion versus we want to figure out the average number of overtime hours worked. That's going to be means. All right. But there's even the key word in here. I mean, you even see that it says average spending. So this is going to be a means. So you're going to use that same formula that we just used. We're just going to put in different values. You see your sigma is 60.5. 99% confidence level means that our alpha is 0.01. So the z-score we're going to need is going to correspond to 0.005. And then we want our estimate to be within $1. Well, that $1, that's our error bound for the mean. It's our EBM. So the struggle for sure is to first figure out, which we're doing, proportions or means. Then it's sifting through, like any word problem, it's sifting through and finding our information. That's done best by practice and going slow. So when people ask me about stats, they're like, oh, stats hard and all that. I'm like, well, it's not really that hard if you're okay with word problems. And then that's usually when everybody gets that look on their face and goes, because stats is just one big word problem, right? All these things are word problems. Once you figure out what it is, okay, you just fire it into the formula. But you have to be able to recognize what formula it is from the words, and that is challenging. So, all right. So hopefully that's good for chapter 8. It appears that at least Caroline is happy with that. So let's go take a look at the from chapter 9, looking at hypothesis testing for the single population mean. And so let's just look at the first one. All right. The average fruit fly will lay 423 eggs into rotting fruit. Yay. Hope nobody's eating dinner right now. A biologist wants to see if the average will be fewer for flies that have a certain gene modified. Okay, so the data below shows the number of eggs that were laid into rotting fruit by several fruit flies that had this gene modified. Assume that the distribution of the population is normal. Okay, so what can be concluded at the alpha equals 0.05 level of significance? All right. So important we say it twice. All right. So let's just kind of work through this. So first it says, for this study, we should use t-test for a population mean, z-test for a population proportion. All right, which is it? Is this a mean or a proportion? Are we looking for the average number or the percentage of? Well, so Ceremony, I see, just put in mean into the chat box. As did Branda. Okay, I agree. This is definitely going to be a mean, right? Because, I mean, even tells us, the biologists, they want to see if the average will be fewer for flies. Okay, so we're doing a mean. Why is it a t-test as opposed to a z-test? I mean, yeah, they didn't give us the option for z-test, but even if it weren't an average, how do you know this has to be a t-test and not a z-test? Yeah, good, Willie. There's no standard deviation. We could calculate a sample standard deviation, right? You could put this data into your calculator and say, calculate. But we definitely don't know the population standard deviation, so that's why it has to be a t-test. Okay, so the null hypothesis, null and alternate hypothesis should be, well, I'm going to start here with, these should be mu's, because we're testing means, right, as opposed to proportions. All right, so we've got equal, greater than, not equal, less than. Which one does the null hypothesis get? And I'm going to tell you, this is pretty easy because it always gets the same thing, the null hypothesis. Yeah, thanks, Willie. It always gets equals because the null hypothesis is always that the two are the same. So that in this case, that the sample is a good representative of the population. Okay, so null hypothesis is always equal. But then that's where the alternate hypothesis comes in. Which one does it get? Now, I will tell you that the one it will never get is equals. But it could be greater than, equal, not equal, or less than. So let's see what we're doing. So Willie, you say fewer. Why do you say fewer? Suggesting less than. What makes you think that? Yeah, it's in the problem, right? If you read it, you see, right, the biologist wants to see if the average will be fewer for flies that have a certain gene modified. So this is what they're really interested in. They're really interested in seeing, is it actually less than? So, and what it's going to be less than, hopefully, is 423, which was the, if you come back up here, right, that was the average from before. So, right, so we want the average fruit fly. Okay, so for both of these, we want those to be 423. So the null hypothesis would be that the mean does equal 423. And the alternative hypothesis would be that actually, no, the mean is less than 423. All right, so let's keep going here. So the test statistic, it is a t-score. The question is, what does that equal? And then we also need to calculate the p-value and so on. Now, this is where I'm going to go to the calculator. So let me real quick write down these numbers. Let's see, we have 392, 421, 416, 431, 393, 426, 429, 416, 417, 424, and 438. Okay. So let's go to the calculator. Let me switch my view here for you. And let's put this in. All right, so first things first, we need to put this information in. So I'm going to hit stat and then edit. And this is where I can actually put in my data. Okay, so I've got 392, 421, 416, 431, 393, 426, 429, 416, 417, 424, and I believe, oops. Hold on, what's going on? My calculator just froze on me. Isn't technology awesome? Hold on a second here. Let me uh-oh. I can't even close that window. Oh, I broke my calculator. All right. Well, crap. Let me try doing something else here real quick. So I apologize. Give me a moment. Maybe we can actually get this thing figured out. I'm trying to do the classic turn it off and turn it back on again. Okay, so I think we're good. Let's try this again. So everybody with me still? Good. All right, so can you see the calculator? Just give me a thumbs up in the window if you can. Yep, okay, awesome, thank you. All right, so let's try that again. We're gonna go to stat. We're gonna edit. It's just as if it had never happened. All right, so let's try this again. So 392, 421, 416, 431, 393, 426, 429. Oh, you are kidding me. All right. Hey, technology is awesome until it's not. All right, so here's what you're gonna do. So you're gonna put that stuff in, and then you're gonna do a t-test. All right, I'm gonna go ahead and actually do it on my calculator here, just so that we can actually get some numbers. I apologize for the issues, but what can you do? All right, so just give me a second here while I fire all this stuff in. I actually think I might have been going too fast for the calculator, because I can type it in a lot faster on a keyboard than on a Put it in the calculator. Okay, so let me see if I got them all in here. Okay, I think I got them. All right, so I got my information. So I'm going to do a test. Now, I wish I could show you this, but we're going to do a t-test, because again, we're doing a t-test for means. You're going to tell it that you want to put in the data. You're going to tell it where it came from. And you're going to tell it what your mean that you're testing against is. So let's actually go back to that. I can at least show you that. Right, so we had the 423, that is the mean that we're checking against. And then it's going to also ask you what you want your hypothesis to be, what your alternate hypothesis to be. And this is the one where we want to go with, we want mu less than mu naught. Okay. So make sure that you get that all set up properly. So let me just get all my things. Okay, so I hit calculate. And what's lovely about this is it spits out everything. It gives you a t value. It gives you a p value. All right. So what I got when I did this, it spits out a t of minus 1.03865. Oh, wait, to 3 decimal places, 039. Now, before we move on to the p-value, think about what this tells us. Remember, the t statistic is like the z statistic. And so it's telling us how far away we are from the mean. So we're at negative 1.039, so we're smaller. And we're out at negative 1.039. All right, so we're a little bit more than one standard deviation, basically, away from the mean. Okay, so then the p-value that it spit out for me was 0.1617 to 4 decimal places. And this is what we're going to use to let us determine what we should do. All right, so we know this p-value is bigger than alpha. Right? They told us that alpha was 0.05. So this p-value is bigger. All right, so the question then is, what should we do? Do we accept the null hypothesis? Do we fail to reject it? Or do we reject it? So what's it going to be in this case? Go ahead and type into the chat box or yell it out. All right, well, let's see if we can reason this out then. Think about that 0.1617. That's 16%. What that means is that 16% of the time, if you were to go randomly look at a sample of size 11, you would get a result like this. 16% is around 1 out of every 6. So is that rare? Is this a rare event? What do you think? Is 1 out of 6 rare? Kinda. I would answer no. I mean, think about it. That's rolling a die. Like, what if I said, you are going to get an automatic F for this class if you roll a die and you get a 1. Would you be willing to take that chance? Hopefully not, right? Because that's like, whoa, that's too good of a likelihood of me actually failing this class for no reason other than a 1 came up on the roll of this die, right? So I would say that that's not very rare. So basically what that's telling us is that if the null hypothesis is true, if the mean is actually the same for these fruit flies that have this modified gene, then there's a 1 out of 6 chance that I could have gotten this as a sample. I think that's pretty likely, right? So I'm not confident that the null hypothesis is wrong. For me to be confident that the null hypothesis is wrong, I need that p-value to be small. Small. Right? And that's what the alpha does. When we say we're going to let alpha be the 0.05, that's telling us, okay, how small does small have to be? I need to be less than that. I need a p-value less than that for me to feel good enough to say the null hypothesis is wrong. Okay, so because the p-value is bigger than alpha, I don't think the null hypothesis is wrong. So I'm not going to reject it. Okay, we only reject if our p-value is less than alpha. Okay, so I'm not going to reject. So then, do I fail to reject or do I accept the null hypothesis? Which of those do I do? Because believe it or not, they don't mean the same thing. Right? Because accept means, yep, the null hypothesis is right. Fail to reject means I haven't seen anything that makes me think that it's wrong. Right? Which is different. If I tell you, hey, you know what, Kira, you're right. That's different than me saying, you know what, Kira, I don't know that you're wrong. It's very, very different. There's very different. It's like in sports. So if you're watching like replay, right? When they say, well, the replay confirms versus the play stands, right? It's kind of the same deal here. And so when we do hypothesis testing, we never, ever say, Kira, you're right. We don't do that. We say, Kira, I don't have evidence to show that you're wrong. Okay, that's just the way that it's done. That's the phrasing that it's done. And so what we're going to do is we're going to fail to reject. So you can only do one of two things with hypothesis testing. You either reject the null hypothesis or you fail to reject. You either say you're wrong or I don't have evidence to suggest that you're not wrong. Okay, so it's kind of a weird, don't blame me. All right, I didn't make up stats, but this is how it's done. All right, so since our P is bigger than alpha, we're going to fail to reject it. Okay, so let's see what this says, or which of these statements we want to use as our final conclusion. So the data suggests the population mean is not significantly less than 423 at alpha of 0.05. So there is sufficient evidence to conclude that the population mean is equal to 423. All right, or the data suggests the population mean number of eggs that fruit flies with this gene modified is not significantly less than 423. So there is insufficient evidence to conclude that the population mean is less than 423. Or the data suggests the population mean is significantly less than 423. So there's sufficient evidence to conclude that the population mean number of eggs fruit flies with this gene modified will lay in rotting fruit is less than 423. All right, well, it's definitely not the last one because we don't have evidence that it's less than 423, right? In fact, we're not willing to throw away that it's equal. Okay, so which of these first two is it? Is it there's sufficient evidence to conclude that the mean number is the same? Or there's insufficient evidence to conclude that the mean is less? So which of those is not saying, which of those, remember what we want to do. We don't want to say, Kira, you're right. We want to say, Kira, we don't have evidence to show that you're wrong. So which of these statements is the, Kira, we don't have evidence to show that you're wrong? Well, it's the second one. Because look at what the first one is. It's saying there's evidence that it's equal to 423, that this hypothesis is correct. So that's the, hey, Kira, you're right. But that's not the way we phrase it. We phrase it as, we're not convinced that you're wrong. We don't have evidence to show that you're wrong. So it's definitely a roundabout kind of way. But this is the process for these kind. When you have data, you want to put it into your calculator as data and let it run it numbers for you. I'm going to guess, let's go take a look at, let's see. Okay, so like this one is not one where you're going to put in data, right? So it says nationally, patients who go to the emergency room wait on average 6 hours to be admitted. So then we want to know, do patients at rural hospitals have different waiting time? So we're going to look at 13 patients, average of 5.2. The standard deviation for these 13 patients was 1.7 hours. What can be included at the 0.1 level of significance? Okay, so again, are we looking at a proportion or a mean? Well, it's a mean, and it's a t-test again, because we don't know population standard deviation, but we know sample standard deviation. So null and alternate hypothesis are both means. That guy's equal, and we want to see if it's equal to the 6 hours. And this one we were saying, do patients have a different waiting time? Okay, so which one are we going to use? Greater than, less than, or not equal? If what we're wanting to test is a different waiting time. Which of those three means different? Good, it's not equal. So that one we're going to do not equal to 6. So now when we go to do our test, you know what, I'm going to see real quick if my calculator has come back to life. It has not. Okay, never mind then. But anyway, you're going to put it in, still doing a t-test, but now you'll put in these numbers. You'll put in the number of people, what their average was, what their standard deviation is, and run the thing. So you'll still get a t statistic. and you're going to get a p-value, and then again you're going to look and see is that bigger than or less than. So it's just a matter of what you put in. All right. So here's what we're going to do. Let's take a real quick break because I've been talking for a while. Let's come back at the top of the hour at 5 o'clock. I'm going to see if I can get my calculator issues fixed because I want to be able to show you at least one of these all the way through. So you can see what you need to do in your calculator. So come back in 10 minutes. You'll know I'm ready when I show back up on the screen. Yeah, I'll see if I can get this fixed up. All right, so I'll see you guys in just a few. Okay, so I think I figured out the calculator issues. So let's see if we can go back and do that problem. So let me remind you what we're working on. We were looking at this one about the patients that are at rural hospitals. And we want to see if their waiting time is different than what it is for just the overall. So well, let's take this information and let's actually go and put it into the calculator so that you can see how this is done. Okay, so let me go ahead and show you that. So we'll go back to the calculator, man, cross your finger here. All right, so this one, since we're not putting in data, we're still gonna go to stat, but let's just jump to the test. So we're gonna do a test here. And hopefully you remember that it is a t-test because we weren't given population standard deviation. We were given the standard deviation of our sample. So we're going to do a t-test. All right, so we're going to leave it as stats. We're going to leave it like that. But now we're going to put in the mean, like what we're testing against, right? And what we're checking against is the mean of 6. If you go back and you look at the question, it says that on average, people have to wait 6 hours. So that's what we're testing against. Now the X bar, that's our sample mean. So that's where we're going to put the average for the folks that we tested at rural hospitals. And that was 5.2. And then we had a standard deviation of 1.7. All right, and then we're going to go ahead and put in the number of people in our sample, which was 13. And now we're going to choose which of the alternate hypothesis we're going to use. And this was not equal. If you remember, it was saying we want to know if it's different for people that go to rural hospitals than to just in general. All right, so it's that easy. We hit enter and it spits us out numbers. So again, remember this asked for a t-score. Well, now we've got our t-score of minus 1.696. We have a p-value of 0.1155. And so let's go see what that tells us in terms of the homework set. What we need to do here. Okay, so we'll go back to the homework page. All right, so the t-statistic, it was minus 1.697 if we round it to 3 decimal places. And then the p-value was 0.11 is all I remembered off the top of my head. And then 5.5 were the next two numbers. All right, so this is a calculator exercise, right? At this point, you can do it without a calculator if you want. You don't want. Don't do that. put this into the calculator. Let it get you your T and your P. All right, don't do it by hand. All right, so again, this p-value, this is bigger than alpha. So what do we do with the null hypothesis? We really only have two choices, right? Because we never accept. Do we reject it or fail to reject it? All right, so Willie says we reject the null hypothesis. No, so now he just changed his mind to fail to. So fail to, actually. So again, in order for us to reject, or wait, we'll let Willie continue to vacillate between the answers here. Yeah, so again, remember what we need to reject it. We need this to be a rare occurrence. We need our sample to be strange. Has to have a small p-value. And this is not, right? 11%, that's 1 out of 9. 1 out of 9 is not that small, right? But it's definitely not less than the alpha, right? We wanted a 10% level of significance, a 0.10 level of significance. This is bigger than that. So that means we're going to fail to reject. If p is less than alpha, reject. If p is bigger than alpha, we fail to reject. All right, so what that means is that the null hypothesis could very well be true. We don't have evidence to suggest otherwise, right? So again, this is we're not saying, hey, guess what, Willie, you're right. We're saying, well, Willie, we don't have evidence to show that you're not right. Okay, but let's see which of these that is. So suggestion the population mean is not significantly different. Okay, so it could be that one. It's definitely not this one because we don't have evidence that it is significantly different. This also is not. All right, so there's statistically insignificant evidence to conclude that the population mean is different than 6 hours versus statistically insignificant evidence to conclude that the population mean waiting time is equal to 6 hours. All right, so we don't have proof or evidence that they're equal, but we don't have enough evidence to suggest that they're different. Yeah, okay, so we're not sure that Willie's right, but we're pretty sure he's not wrong. All right, so that's what it looks like when you go into the calculator, and I wanted to make sure you saw the actual keystrokes and what to do. Let's get our points while we're here, by the way. So, yay. All right, so there you go. All right, well, so with hypothesis testing, again, some key things. We're either rejecting the null hypothesis or we're failing to reject it. We can be making errors. Remember, we talked about type 1 errors and type 2 errors and all that. So we might be making errors, but the alpha is making it so that it's less likely that we commit the type 1 error. So, but you've seen the process now. You take your numbers, you put it in the calculator, it spits out a p-value, and then you use that p-value and compare it to what level of significance you need, and then either reject or fail to reject. And just so you know, the alpha, that's going to be given to you in general, and how that's determined is really determined by the person who's doing the study. Right? Like when you end up doing a study, because when you do project 2, it's going to be a hypothesis testing project. you're going to create a hypothesis that you're testing, and you're going to determine the level of significance. Okay, so that's determined elsewhere before you do your study. Then you just let the numbers play out what the numbers say. In general, the 0.05 is a pretty standard level for alpha. That's probably the most common one to see, but it's not at all standard. It really depends. Okay, well, with our remaining like 45 minutes, I do want to start showing you how we compare two samples. So I'm going to head up to the whiteboard real quick, and I will see you in a second. All right. So we've now seen how to test one sample against a hypothesis. But where we want to go next is how do we compare two different groups? What if I want to look at two different groups and see if their means are actually the same or they're different? Right? Like, for example, we could do something like, all right, I want to check IQ levels of students at the college. Remember President DeFranco was thinking you guys were above average and all that. Okay, so he started looking at it and going, you know what? I actually think that there might be a difference in IQ levels between students at Lake Tahoe Community College and those at Western Nevada Community College down in Carson. Okay? And so what we're going to do, he says, hey, Bruce, help me out. Do a study for me. I want to find out, like, I think our students are smarter. Cool. I'm with you, Jeff. Let's do this. So I go to LTCC. I randomly select a handful of students, a certain number of students, and I check their IQs. And then I go down to Western Nevada and I do the same thing. So the question is, how do I compare those two? What's the process so that I can actually do an, as they say, apples to apples comparison between the two groups? Right? Okay, so that's what we're talking about, is looking at comparing two. So there are really two things we can do. We can either compare means of two samples, or we can compare proportions. And so this is the same idea as we've had all this time, right? Where we have multiple possible ways of things that we're looking for. And we're going to have to do them each separately. So I'm going to start with the comparing of the means of two samples. There's no way we're getting to proportions today. So we'll just look at means and we'll save the proportions for next time. Okay, so basically what we're going to have sample one. And for sample one, we're going to be able to calculate some numbers, right? There's going to be an average. So I'm going to write this as the bar, X bar, but with a little one, meaning it's coming from sample number one. Right? We're also going to be able to calculate a sample standard deviation from sample one. We might know a population standard deviation for sample one. We'll definitely know how many we sampled. So notice that what I do is I'm using the exact same symbols. I'm just putting a little one below them so that we know they're coming from sample number one. So maybe that's the Lake Tahoe students. And then maybe sample number two is my sample from Western Nevada down in Carson. And I'm going to be able to do the same thing. Okay. So some things to realize. First of all, the sample sizes don't have to be the same. All right. It's not necessary that N1 and N2 are equal. So when we do a sample, we don't necessarily need to have the same number. There are certain types of tests and things that we'll do where we do need them to be the same, but in general, we don't. Right? I could ask 40 students in Tahoe and 35 students down in Carson. That's okay. Right? So we don't need N1 and N2. Like always, these guys may not be known. We may not know the population standard deviations, and in fact, in general, you don't. And we can always get our sample standard deviations, but the population standard deviations we may or may not know. Okay, so those may not be known. All right, well, what we're going to actually test, what our variable is going to be, is actually going to be the difference in the means. So this one might feel a little bit weird because every time we've done anything up to this point, we've just been testing the means. But this one, we're going to be looking at the difference in the means. It's going to be x1 bar minus x2 bar. And here's why. Here's why. Think about what our hypothesis is going to be. The null hypothesis is going to be that mean 1 equals mean 2. Mean 1 and mean 2 are the sample or the means for populations 1 and 2, right? So the Tahoe students or the Carson students. But whenever we've done a hypothesis test, we've always had something equaling a number. And these things are both changing. So if you were to just do a subtraction, do some algebra, this turns into mu1 minus mu2 equals 0. And so it's this thing that we're comparing against a number, which is what leads us to the variable we're looking at is actually x1 bar minus x2 bar. So that's what we're doing when we compare means from two samples. We're actually going to be looking at the difference in their means. So here are what the two hypotheses are going to be then. Your null hypothesis is going to be that mu1 minus mu2 equals 0. And then your alternate hypothesis will be, well, not equal to 0 or less than 0 or greater than 0. Again, we're going to be able to pick which ones of those we want, depending on what the question is. But it's always going to be, we're going to look at the difference in the two means. All right, so cool. Big deal. Well, that sort of drives everything else in terms of finding the standard deviation, finding the z-scores, all that good stuff. Now, I'm going to show you, you don't have to write this down. I'm going to show you what the standard deviation actually looks like and how you calculate a z-score if you were to do it by hand. We are never going to do that. We are always going to use the technology. All right, and it's going to automatically do this for us. But this is how nasty it gets. All right, so here's your standard deviation. if you actually wanted to calculate the standard deviation here, what you have to do is this. You take the population standard deviations, square them and divide by your sample sizes, and then take the square root. And this gives you the standard deviation for this distribution, the distribution on x1 minus x2. So by choosing it to be a difference, it makes the math way worse. All right, that's your standard deviation. If you were going to do the z value, get your z score, right? Your z score, check this out. So take the difference in those, and then you see how far away that is from the difference of the actual means, and then divide by the standard deviation. Yeah, okay. So that's what you would have to do if you were going to do it by hand. Of course, we're just going to say, yeah, let's use the calculator. Okay. So it's a seemingly easy idea. Just looking at the difference of those means. We want to see if the difference in them is 0. So they're the same. By turning it into that distribution, though, it gets kind of gnarly. All right. So we are just going to use the calculator. But let's think about what are the conditions necessary in order to do a z-test. All right. So this is what we need. For a z-test. Okay, so the first thing is that we need both samples to be random. Okay, so they have to be randomly selected. No big deal. That's pretty much been the standard case for everything. Okay, but both of them need to be random. They both have to be independent. That the one doesn't affect the other. So they have to be independent of each other. But then this is the more important one. Is that you need to know the population standard deviation for both populations. If you don't know it for one of them or both of them, then you have to do the t-test instead of the z-test. But as we've seen, it doesn't really change much other than you go and you press a different button. The underneaths of it are very different, but the functional side is not. Okay, so let me show you how this works, because it really isn't that bad. Once we see what we're plugging in, where we need to go onto the calculator to actually put in our information. Okay, so let's do this. Let's actually test. Right? We're going to look at the IQs of students at Lake Tahoe Community College, and we're going to compare them to students at WNC, Western Nevada. We'll have a little cross-state rivalry, which for those of you who are not like in the Tahoe area, this is not a real rivalry. We talk about the people at all ever. So anyway, so we're gonna look at this. So let's say we sample 25 students at LTCC and find an average IQ of 107. we sample 33 students at WNC and find an average of 103. And we'll say that the population standard deviation for both is 7. Okay, so maybe we just know, like, in general, students, they're going to have this standard deviation. All right, so here's the question. We want to know, do LTC students have higher IQ? Let's test at the alpha equals 0.05 level. All right, so there's your standard kind of question, comparing two means. So let's sort of sift through and find all the information that we're going to have to put into the calculator. And also, let's write our null and our alternate hypotheses. So we'll start with the null hypothesis. And the null hypothesis is that mean 1 minus mean 2 is equal to 0. That's always going to be your null hypothesis when we're comparing two means. Just to help us out so that we can reference it later, it's probably good to determine which is group 1 and which is group 2, because it doesn't matter. I'm just going to call the LTCC students group 1 since they were the first one we ran into. Okay, so LTCC, that'll be number 1, and WNC is going to be number 2. Just so we've got that for reference. Okay, so now let's think about the alternate hypothesis. So I just put there mu1 minus mu2 because it needs to look the same as the null hypothesis. And I also put 0 because we're comparing it against 0. But I left a spot for, do we want greater than, less than, or not equal? Okay, now this one, we have to go back and look at what are we testing. We're looking to see, do LTCC students have a higher IQ? Okay, so if they do have a higher IQ, what are we going to get when we take the difference? When we take the Tahoe students and we subtract off the Carson students. If this is true, is that number going to be positive, negative, or does not equal? So Willie put in the chat box, thank you for that, greater than. That's what we're trying to see. We're trying to see, this is the average for Tahoe bigger than the average for Western Nevada. So is the difference greater than 0? Okay, so there's our null hypothesis, and there's our alternate hypothesis. And let's just start writing down all of the things that we know that we can get from it. Okay, so we sample 25 students at LTCC. That tells me that N1 is 25. We found in that sample the average was 107. So X1 bar is 107. We sample 33 students at Western Nevada. So N2 is 33. And we found an average IQ of 103. All right, so X2 bar is going to be 103. The sigma for both is 7. And then the last thing that matters is the alpha level. I'm just going to put a box around that just to remind us when we come back to it. We're going to look at the 5% level. Whew. Okay, so there's all the information. Now, if we were doing this by hand, we'd have to go to that formula, calculate standard deviations and all right. Instead, let's just jump to the calculator. All right, so I'm going to go ahead and share my screen again, and I'm going to show you the steps you need to take in order to do this on the TI-84 Plus. Again, whatever version you have, the calculator should do something similar. Okay, so we want to do a test again. So this time, though, it's a hypothesis test for 2 means. So we're going to go to stat, go over to test. All right, so looking at this list, I bet you can guess which one we're going to do. We're doing a Z test because we've got standard deviations, but I'm not going to do the Z test. I'm going to come down here to do the 2 Samp Z test. Two samp means 2 samples. So when we were doing this before, just a regular old T test or Z test, use one of these. But when we're going to compare 2 samples, we're going to jump down to either 2 sample Z or 2 sample T. Okay, so now we're ready to put stuff in. This one we don't have data. We're just going to put in the stats. But let's see what we got. So we need first the standard deviations for both populations. And in this case, they were both 7. All right, so X1 bar, that's the average from the first set, which was 107. And then we need N1, well, the number of people we sampled were 25. All right, so then we go to X2 bar, the average for our second sample, which was 103. And then we need the number of our second sample, which was 33 of them. All right, and now we have to get our which test we want to do. All right, now notice what this says. If you look over on the left, it says mu1. So this would be mu1 does not equal mu2. No, that's not what we want. We're actually trying to see if mu1 is bigger than mu2. Right? We want to know our LTCC students, do they have a higher IQ than the Western Nevada kids? All right, so mu1 is greater than mu2. I'm not going to draw it, so I don't care what the color is. So now I hit enter and I let it do its thing. So you can probably see now why I wrote down all that information. It helped to sift through everything to find those values, but I also needed them to punch in. So I let it do its thing. And this is what we calculate. So I'm going to go ahead and write those down real quick. The z-score, not super important, but you know how they like to ask you about the z-score, but more importantly is that p-score. All right, so that's what our calculator tells us. Now let's talk about the consequences. All right, so hopefully you're all seeing this. Not that big deal, right? Put it into the calc. It's just a matter of going to the right place. To Samp Z. Okay, well, what does this actually tell us then? So we look at the p-score. We're going to do the same thing with the p-score that we did for the one sample. We're going to compare that to alpha. So how does this compare to alpha? We come back and we look at what we wanted our alpha to be, was 0.05. And so we've got that p is less than alpha. Okay, so what does that tell us to do? Are we going to reject or fail to reject the null hypothesis? What did we do before when p was less than alpha?
Is it reject?
That's perfect. Thanks, Kira. Good job. So we're going to reject H naught. Okay, so this is a rare occurrence. 1% of the time, if that null hypothesis is true, this would only happen about 1 out of every, what's that? 1 out of every like 90 sometimes. That's weird. That's uncommon. So that makes me think the null hypothesis isn't correct. Okay, so we're going to reject the null hypothesis. So then what that would mean is, okay, we think that this is no, we don't think they're actually the same. Right? So here's what we can say. We can say that there is significant statistical evidence to suggest that LTCC students have higher IQs than WNC students at the 0.05 level of significance. And that's how we would want to write this. Right? We did find evidence. We found enough evidence to reject H naught. So that means that we don't think they're the same. What we tested was greater than. So we've got enough evidence to suggest that LTC students do have higher IQs than Western Nevada students, but we always want to include at what level of significance. Because, for example, if we had made it so that we wanted a alpha equaling 0.01, so we wanted a 99% level, we wouldn't have done this. We wouldn't have rejected H naught because this is bigger than 0.01. So you always need to say at what level of significance you are looking at. Otherwise, it doesn't make sense. All right, so if this were the sample that we did, I would go back to Jeff DeFranco or the college president and say, hey, Jeff, okay, you asked me to go do this. Here's what I did. I sampled 25 random students at our college. I went down to Western Nevada. I sampled 33. I know the standard deviations are 7 from this national study. And my data gave me these numbers. So I did a 2-mean comparison, and I found significant evidence statistically to state that Lake Tahoe Community College students have a higher IQ than Western Nevada college students. So then he goes, cool, that's what I thought. I'm going to put this study into a grant, see if we can get some more money, blah, 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 right? And that's how that would play out. All right, well, hopefully you're seeing that's not that big of a deal. It's just a matter of picking out all the information and putting it in. All right, but this was for a Z test. And unfortunately for Z tests, they're rare. We rarely use them. More often we use t-tests, right? Because t-tests, that's when we don't necessarily know standard deviations. So let me give you an example of a study that I want to do. I have no idea how this is going to play out, but this is using real world data, and it's something that I'm a little bit curious about. All right. So here's what we're going to do. If you're not a sports person, it's okay. It's not that big a deal here, but this is sports. So in baseball, it's my favorite sport. In Major League Baseball, there are 2 leagues. There's the American League and there's the National League. And traditionally, it's thought that National League, or that the American League, has more home runs because of the fact they have what's called a designated hitter and all this. But it's kind of a held belief that the American League hits more home runs than the National. All right, so here's what we're going to do. We're going to look at last year's data. And we're going to look at the 10 players who hit the most home runs in each league. And we're going to see, does that mean that on average, there are more home runs hit by American League players or National League players? Okay. So let's see how this is going to play out. So do AL hitters hit more home runs on average? Okay, so that's what we're going to do. So this isn't exactly a random sample. Just run with this though. So what we're going to do is we're going to sample 10 from each league. To compare. All right, but I have no idea what sigma is. I couldn't even begin to guess what a standard deviation for home runs hit is. Okay, so we're going to do some real numbers here. So here's what I got. In the American League, the 10 that we sample give us 22, 19, 17, 17, 16, 16, 14, 14, 14, and 14. The National League, we have 18, 17, 16, 16, 16, 16, 16, 16, 15, and 15. But it turns out it's the 10 highest. All right. Let's see. Now, before we actually do this, we need to specify a level of significance. And so I'm going to go ahead and go with, let's do alpha being 0.05 again. So we'll do it at the 5%. All right, so before we just jump into the calculator and do this, realize that because of the fact we have no idea what sigma is, we need to do a t-test. And let's also write down our null and alternate hypotheses. So the null hypothesis, again, is that the difference in those two is equal to 0. And then the alternate hypothesis, if we specify them as groups, we'll just go ahead and do them again in order. A will be number 1 and L will be 2. Then we think that American League hitters hit more. So that means that mu1 is greater than mu2. So mu1 minus mu2 is greater than 0. All right. There you go. Let's see what this has to say. So I'm going to share my calculator again. And let me show you the process here. Now, this is one where we are going to have to put in data. So let's go to stat. Let's edit. And I'm actually going to put these into different lists. So maybe calculator doesn't get mad at me. Okay, so we'll make list 3 here be the American League number. So I've got I'm trying to go a little bit slower because I think that was the issue before. We'll find. All right, so there are my 10 American League home run numbers. If someone just take a peek at those and see if they look right. And I'll start putting in my National League numbers. Okay, so I think I got it. All right, looks good to me. So we've got list 3 is the American League and list 4 is the National League. All right, so now let's go to stat. We're going to do a test. All right, so again, it's a 2 sample, but this time it's a 2 sample t-test. It's a t-test because we have no idea what this population standard deviation. Okay, so it says, do we want to do data or stats? I want to do data. So I need list 3 and list 4. So again, if you don't remember, those are little secondary buttons. So you do second L3, and then second L4. It's really nice because you can put all kinds of data in there and hold on to them. The frequency for both of my lists is 1, right? Because I'm not using a frequency table or anything. And so those both get the 1s. And then in terms of how I want to compare these, I'm looking for, is mu1 bigger than mu2? So looks like what I want. Now, if you look at this next line, it says pooled. When we pool data, and we will do this on certain occasions, that's where we put all the data together into one big group. We don't want to do that here. So we're going to leave this as not pooled. And then we're going to come down here and we're going to calculate. All right, so you can see there a t-score. You can see a p-score. You also see degree of freedom. Because this is a t-score, there is a degree of freedom. But notice that it's, before it was n-1, which in this case would suggest 9. It's not 9 because this is a different kind of t-test. This one, don't worry about calculating the degree of freedom. It's a horrible, nasty thing to calculate. And the calculator will spit it out for you. Just realize that it's different. But here are means. So X1 bar, there were 16.3 home runs on average for the top 10 AL hitters, 16.1 for the NL hitters. There are sample standard deviations. Both our sizes were 10. Okay, but the important number is this guy right here. Right? We got a P equals 0.41176. All right, well, let's come back to the whiteboard. All right, so we calculated P as 0.41176, which means that P is greater than alpha. Again, think of this as like a percentage. This is saying that if the null hypothesis is true, we would get a result like this 40% of the time. Okay, that's really frequent, right? Almost half the time this would occur. So what this tells me then, again, since P is greater than alpha, I'm going to fail to reject H naught. So here's what my statement's going to be. I'm going to say that there is not significant statistical evidence to suggest that there is a difference or there is a difference between leagues in hitting home runs, blah, blah, blah. Right? But there's just not enough information for me to say that they're different. Are they the same? No, I don't know about that. But it definitely doesn't look like the American League hits more home runs on average than the National. And I certainly can't say that. I should probably put here that alpha equals 0.05. But I could have actually a really big alpha and still be pretty confident that there's not much of a difference. Okay, now if we really wanted to be good about this and we really wanted to see if there was a difference, we wouldn't look at the top 10 home run hitters in each league. We really would randomly select. We might want to make some sort of a limitation on how much they played, right? Like if you have like somebody who just played one game, probably don't want to keep them in the mix. But if you just said, okay, all players that played at least, 2/3 of the season, or something like that, randomly pick those, and then that'd probably be better. But this is how you would do it with real numbers. So at least when it comes to the top home run hitters, American League, National League, didn't appear to matter last year. There you go. Stats in action. All right. I think we're pretty much out of time, so I'm going to go ahead and call it for today. But just a couple things to remind you about. We do have homeworks that are due tonight. Don't forget to get in there and work on those. Those are due tonight at midnight. And we're also going to have a quiz next time, our usual Thursday quizzes. And the content on this one, let me think about what it should cover. Because the last one was on chapter 7, right? Central limit theorem and confidence intervals. Yeah, okay, so this one, the quiz on Thursday, it will be on chapter 8, at least the part on confidence intervals with proportions. And then chapter 9. And chapter 9 was hypothesis testing, but just for one sample. All right, so this is one sample hypothesis tests. Okay, so that'll be on Thursday. We'll do the same thing as always. It'll be available at 3:30, and then we'll start class at 4. And we'll continue talking about two population, two sample tests, and we'll move beyond mean. We'll look at proportion and see how those are done as well. All right, so with that, have an awesome couple days, and I will see everybody on Thursday.